Recording in
All right, so tonight we're going to pick it up where we left off with chapter 5. And so what we're going to be introducing here is some very important probability distributions that are heavily used in business applications. And so we'll start with the binomial distribution. And the name kind of gives us a hint as to what it's all about. This is a case where we have some kind of an experiment taking place, and there are trials. Each time we repeat this experiment, we call it a trial. Okay. There are n of those trials. And the key here is that the trials are independent of each other, meaning that the outcome of one trial does not affect the ones that follow it. In addition to that, on each trial, there's only two possible outcomes, which we'll call success and failure. And it's the two part that gives this distribution its name, binomial. Okay, so there's a reason why it's called binomial is because for each trial of this experiment, there's only two things that can happen, and we'll randomly choose one of them to be success and one to be failure. It really depends on what we're trying to find out. So then we're going to call the probability of success P and the probability of failure 1 minus P. And of course, since there's only two probabilities, they have to add up to 1. We'll have P and 1 minus P. And these probabilities are fixed or constant throughout the entire experiment. Okay, so that's a lot of assumptions. If all these assumptions can be met, then there's a special formula we can use to calculate probabilities rather than having to do it ourselves by looking at the sample space, which could be very time consuming if we have enough trials of the experiment. So let me just repeat those one more time. A binomial experiment, as it's called, has the following properties. Oh, before I continue any further, I just want to mention that the binomial distribution is a discrete probability distribution, which means that whenever we repeat this experiment, there's only a finite number of possible outcomes. So the number of possible outcomes is finite. So if you remember from last time, this is what we mean by a discrete random variable, as opposed to a continuous random variable where the number of possibilities is literally infinite. Okay, so, and then by the way, for the rest of this chapter, we'll only be considering discrete probability distributions. The continuous ones, we're going to save it for later. Okay, so anyway, just to repeat, a binomial experiment has the following properties. Number one, the experiment has or consists of a sequence of n trials. On each trial, there are only two possible outcomes: success and failure. The trials are independent of each other, and we'll do it in the same order they are. The probability of success is P. The probability of a failure is therefore 1 minus P, because there's only two possibilities and they have to add up to 1. And the last step is first to note that, actually, there's one more thing. These probabilities do not change throughout the course of the experiment. And then finally, the last piece is that the trials are independent of each other. So in other words, whatever is happening on this in each trial, it doesn't affect the outcome of the following trials. So the classic example of this is a coin flipping experiment. So imagine the following situation. Suppose that a coin is flipped, let's say 4 times, and we'll define X, which is a random variable, a discrete random variable, to be the number of heads that turn up. Now we know that that means that when we flip the coin, there's anywhere from 0 to 4 heads that can turn up after we flip the coin 4 times. All right, so X can be anything from 0 to 4. So the sample space of this experiment would look like this. Where those numbers represent the number of heads. Okay. Now, does this qualify as a binomial experiment? Okay. Well, number one, actually, I probably should have numbered these. Just so we can keep track of which one is which. N trials is number one. On each trial, there are 2 possible outcomes, success and failure. We'll call that one number 2. Number 3, the probability of success is P. The probability of a failure is 1 minus P. And most importantly, these probabilities do not change throughout the course of the experiment. And then finally, number 4, the trials are independent of each other. So number 1, this experiment consists of a sequence of 4 trials. In other words, each flip is a trial. Number 2, on each trial, there are only 2 possible outcomes. Now, because X represents the number of heads that turn up, it stands to reason that we'll let heads equal success and tails will represent failure. Okay. Then we can claim that the probability of success is P equals 1/2, while the probability of a failure, which means a tail, so actually let me put that in parentheses here. And the probability of a failure, which is tail, is also 1/2. 1 minus P is equal to 1/2. And the key detail here is that these do not change throughout the course of the experiment. Why would they? I mean, because the coin never changes. The coin itself is fixed. It's flipped every time we flip it. There's a 50% chance or half P equals 0.5 of getting ahead, and the same thing for tails. And then finally, the trials, flips, are independent of each other. Okay, in other words, every time I flip the coin, the first flip doesn't affect the second flip, which doesn't affect the third or the fourth or the first. None of them affect each other. Right? So in other words, think about it this way. If you have 3 heads in a row, it does not affect the probability of getting a 4th head on the next flip. Okay, it's still the same 1/2 after no matter how many trials there are and no matter how many heads turned up, the probability on each flip is always 1/2 of getting ahead, regardless of what has happened in the past. So all 4 of the requirements of a binomial experiment have been met. Therefore, this is a binomial experiment, and X is a binomial random variable. So you can think of it as a special type of discrete random variable. So in other words, a discrete random variable can follow many different probability distributions, one of which is the binomial. Okay, so in other words, binomial is a special case of a discrete random variable. Okay, now in the past, up to this point, every time we tried to calculate probabilities, we did it by going through the sample space. Now here, we're not going to do that. There's a formula we can use once we determine that our experiment does in fact qualify as a binomial experiment. That means we can use the formula that I'm about to show you and calculate any probabilities that we need. Okay, now you might say, well, it might be just as easy to use the sample space, but that's actually not the case here. The formula is a little complicated, but we'll be able to use our calculators to get the results that we need. Okay, and by the way, you'll see why, one of the reasons why we studied combinatorics in the couple of sessions ago. Remember, we use factorial and we use combinations and permutations. You'll see again one of the applications of this type of calculations. Anyway, so since this is a binomial experiment, we can use the binomial formula to compute probabilities for all the different possible values of x. And by the way, I'm going to give you a hint right now. These are not all equally likely, okay? The probability of getting no heads, one heads, two heads, three heads, four heads, they're not equal to each other. Okay, so anyway, what is this amazing formula? Well, here it is. And there you go. There's your factorials that I mentioned earlier. We've already seen these. We know how they work. So just a quick review. And just as a reminder how this works, 0 factorial is 1. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1, etc., etc. You might also recognize this expression here actually represents the number of combinations that can be formed when choosing X objects from N. Okay, if you didn't recognize it, that is actually the formula for combinations. Okay, so what we have here in the beginning of our formula is the number of ways of choosing N objects from X objects from N when the order of selection does not matter. Okay, down here we have the probability of a head in this case raised to the X power, and then the probability of a tail raised to the N minus X power. So if you wanted to calculate the probabilities for this particular example that I just showed you, this is how it would work. So for the coin flipping experiment, N is 4, and then P is going to be 1/2, because that's the probability of getting ahead. And then, of course, that implies that 1 minus P would be also 1/2. That's the probability of getting a tail. Now, what I'd like to do is show you how to calculate all the different possible values of x, the probability that x equals 0, 1, 2, 3, and 4, just to get some practice, okay? So we'll start with the probability that x equals 0. And here's the formula one more time. So that means, given that, once again, n is 4, p is 0.5, so is 1 minus p. So for x equals 1, which they're writing, again, don't forget, they're using f. I usually use P because that's what I'm used to, but so we're going to write it like this. F of 0 means the probability of getting no heads. That's going to be, so we plug in the numbers. So if you notice, n is 4, of course, n factorial is 4 factorial, x factorial is 0 factorial, n minus x factorial is 4 minus 0 factorial. The p and p1 minus p are both a half, x is 0. Now this one, I really should write it as 4 minus 0, just to be clear. And now we can simplify it. So if you go to your calculator, you'll see that here, this is actually equal to 1. Okay. Now, if you want to do this directly, you can, but if remember, 0 factorial is just equal to 1. So you've got 4 factorial here over 4 factorial, which is 1, or you can go to your calculator and do. So remember how that worked? We have to go to our special math menu or math app, math. Then we find the submenu prob. And then we go down to number 3, which is NCR. And when you hit enter, it offers you the opportunity to fill in these boxes, which are in this case 4 and 0. Let's see that it is in fact equal to 1. Okay. And in fact, just a general rule, I just want to point out here that as far as combinations are concerned, this equals 1 when x equals 0. It also equals 1 when x equals n. So those are two special cases. Okay. But anyway, so we get a 1 there. Now 0.5 to the first power, 0 power rather, is also just 1. And all that leaves us with is 0.5 raised to the fourth power. And that, if you go to your calculator, is 0.0625. So that is the probability of getting no heads when we flip the coin 4 times. So what about 1? 1 head. All right, so let me copy the formula again. Now you notice each time we do this, the only thing that's actually changing is the x. So we'll have 4 factorial over 1 factorial. Now here it's 4 minus 1 factorial. And then we'll have 0.5 to the first power, 0.5 to the 4 minus 1 power. And now we can simplify it just a little bit. Uh, 0.5 to the first is just 0.5, and then we have 0.5 cubed. So this piece we can get off of our calculator, or we can do it directly, algebraically, but if you do math prob, NCR, this turns out to be 4. So now we plug these back in and we'll have 4 times a half. Now 0.5 cubed is 0.125. And the product of all 3 terms is 0.25. All right. So we do them all exactly the same way. All right. So we'll keep going. Okay. So again, this one is equal to. So you can go to your calculator to calculate that one. It turns out to be 6. So we're going to have 6. This is 0.25, 0.25. And we end up with 0.375. Okay. And then for 3, so we end up with, once again, you put this in your calculators for C3, and that's going to give us 4. 0.5 to the third power is 0.125. And then this is just 0.5. Okay, so when you multiply those out, you get 0.25. And then finally, F of 4. Okay. Oh, you know what? I just realized this. No, this is right. This is it. Good. Okay, so you're going to wind up. This one is, so you're going to have 1.5 to the fourth is 0.0625. And there's our final result. All right, so our probability distribution then looks like this. So let's go back and copy these answers. We'll have, let's see, we had for 0, we ended up with 0.0625. For 1, we had 0.25. For 2, we're going to have 0.375. 3 gives us 0.25. And then finally 4 is 0.0625. Now, interestingly enough, if you look at these numbers very carefully, um, you'll see a very interesting result. Now, my drawing isn't perfect, but if you were to put together a histogram, actually, this is technically a bar chart because the bars aren't stuck to each other, but um, it's going to look something like this. And you'll notice that, what did I do? Here we go. Um, these are the values 0 through 4, and these are 0.0625, which applies to both 0 and 4. Okay, you notice how 0 and 4 are exactly the same. And then 1 and 3 are both 0.25. And then in the middle, we have 0.375. Okay, and so we say that this distribution is symmetrical about it, meaning that if you look at 2 as the center, the left and the right-hand side are mirror images of each other. So this particular case results in a symmetrical distribution. And so you can see graphically, this is what it looks like. All right, now we did a lot of work to get to these results. You're probably saying to yourself, we have these high-powered calculators. It would be nice if we could use those to save ourselves some time. And well, it turns out that there is a way we can do this, which I'm about to show you, but you have to understand what's going on behind the scenes. In other words, you really should not use the calculator until you understand what the formula is doing. So now I'm about to show you the secret of how to do this on the TI-84. So we'll keep the same case, the same coin flipping experiment. So that means that X is the number of heads. Number of trials is 4, P is a half, and 1 minus P is a half. How do I calculate FM0? All right, so here's what you have to do. You're going to hit second, and then the button is labeled vars. By the way, it's up here by the arrow keys. Okay, second vars. Then you scroll down until you get to, in my case, it's letter A. It might be different on yours if you have a slightly older calculator. As long as it says binom PDF, you're good. Okay, now if you notice directly below it is binom CDF. We'll get to that one later on. Right now we're using binom PDF. So then it's going to ask you a series of questions. Trials will be 4. P is 0.5. And then X, this is the part that's different for each case we're looking at. So here we're looking for the probability of getting no heads. So set P X value equal to 0. Now, we already saw earlier that when we used the formula, this gave us a probability of 0.0625. So let's make sure that's working correctly here. So you type in those numbers, All you have to do then is hit enter twice actually, and then look, there it is, 0.0625. All right, let's do one more of these just to make sure we really understand it. All right, so it's the same process. And now the only thing that will change is the X value. This time is 1. Okay, so that's the only part that changed. So when you go back here, as if this wasn't a time saving enough of a device, you don't have to change anything. You can scroll down and just change the X value from 0 to 1. You don't have to retype the number of trials or the probability of success. They're still in the memory of the calculator. Man, they really do make things easy for us, don't they? All right, so change that to 1. And sure enough, it's 0.25. All right, so we don't have to do every single one of them. But you can see that this will probably save us a lot of time. Okay. I mean, not like this till forever, but it took a long time and there's a lot of opportunities for making mistakes. So here it's quicker and it's easier. Now, later on, we'll see how Excel handles the exact same problems. Needless to say, Excel is also capable of calculating binomial probabilities. As a matter of fact, now that I'm thinking about it, maybe I'll show it to you right now. We have the spreadsheet here called um, Chapter 5 Examples. And on the first page, we have this situation where whatever this experiment is, we have 3 trials. Each one has a probability of success of 0.3. So we're going to fill in this probability distribution. There's 4 possible values for X, 0 through 3. And here we're going to put in the binomial probability function. So in Excel, that looks like this. Binom dot dist. Now, if you notice this little ribbon is telling us what we need to provide to the Excel. We have number of successes, number underscore S is number of successes, which is this number right here. In other words, that's the X. The number of trials is D1, but this one needs dollar signs because it's a constant. Probability S is this number here. Once again, we need dollar signs. Oops. Ugh. And then now cumulative, just put 0 there. We'll explain that later on what that means. For now, just put a 0 there and we'll drag it down. Oh my God, that was fast. Now, in order to make sure we didn't goof it up, let's just add these up and we know they have to add up to 1. And if they don't, that means we have a problem. One, beautiful. Okay, now this of course is a different problem. Um, what we could do if you want is we can go back and reproduce the problem we just did here. Um, let's see. Let's do a new sheet for that one. We'll copy this one and we'll just change the, all we really have to do is change the 2 constants. So we'll have 4 trials, 0.5, and also we'll have one more possible outcome, which is 4. Now, if you notice, it filled in everything for us automatically, and it's just those are the same numbers we just had. Not only that, but if we want to create our own plot, we just put insert recommended charts, and what do you know? There it is. Okay, so we've just reproduced we've actually done our coin flipping experiment in three different ways. We used algebra, we used the calculator's built-in functionality, and now we've used Excel's built-in functionality. And of course, they all gave us the same results. All right. Now, you see, the great thing about this too is that if I just want to change the probability of success right here, if I do, it automatically updates itself. I don't have to start all over again. And we could do the same thing here. And again, this is not the same example. You can see here in this case, the distribution is not symmetrical. Instead, you can see that the distribution is positively skewed or skewed to the right just by looking at it. As a matter of fact, what you can do, Excel has a skewness function built into it. So here we should get a 0 or something very close to it. And here, let's see. Oh, I know what happened. This should have been done. Hold on one second. I think I did something wrong here. There it is. Well, let's call this skewed out key. And we'll get exactly 0. No, oh no, not. No, I guess it's not working the way I expected it to. So, all right, we don't need that. It's maybe not working the way I expected it to. So, but anyway, the bottom line is we can visually see here that this one is symmetrical. This one is skewed to the right just by looking at it. So, and by the way, the reason why this is happening is because the probability of success is less than a half, where here it's exactly a half. And if I were to then, let's say, oh, let's try a different case where P is now, let's say 0.7, more than a half. What you're going to see, oh, actually, you know what, I just realized these have dollar signs. They're attached to the numbers up here. We have to update these to indicate that they're coming from these two. So let me fix this. This is now B21. This is now D17. You can see it's now relying on or referring to this cell. And then this D2 is now D18. Then I can drag it down. They'll all update themselves. And then when I plot the graph, you can see, ooh, look at that. It's skewed to the left. So it's just the opposite. All right, so we have all three possible cases skewed to the right, skewed to the left, and symmetrical. Okay, so at least with the binomial distribution, we can make the following conclusions. P less than 0.5 means the distribution is skewed to the right. Okay, that would be this case. And then P equals a half exactly, symmetrical, about the mean. And then P greater than 0.5 means that the distribution is skewed to the left. Okay. Now, they're not going to ask you about this. I don't think they are in MindTap, but it's kind of interesting to see this. So in other words, this is one of the reasons why these graphs are so helpful because they can give us some real insights into this probability distribution. And that in turn can enable us to compare these properties to other probability distributions. Sometimes it's not obvious which probability distribution we should even be using in the first place. And these types of properties can help us make that decision. Okay, so in other words, the whole idea here is that you really should only be using this distribution when you're doing something that in practice replicates this distribution, but it's not always so open and shut which one is the one we're using. So these types of graphs can actually be helpful in that way. Here's very obvious when you're flipping a coin that it's the binomial distribution, but there's going to be a lot of situations where it's not quite so clear which distribution we should be using. Okay. All right. Anyway, what comes next? Oh, by the way, I just realized this example here is taken from the slides. This is the Martin's clothing store, and they're telling us here that they're analyzing the next 3 customers who come in the store, and they know from experience that the customers, when 3 customers come in the store like this, the probability of one of them making a purchase is 0.3. So they want to know the probability that 2 of the next 3 customers coming in the store will make a purchase. So what they're basically asking you to do is this right here. But, we went ahead and calculated all of these anyway to create the entire distribution, but it's the one that they're after is x equals 2. Now they're showing it to us in a few different ways. They're going to show it to us by, well, with logic, with the formula, which you certainly can always feel free to use the formula. Oh my God, they're using this too. Wow, they're really going nuts here. And then finally, they're showing you how Excel does this. And then we, or of course, also went ahead and used the calculators as well. Now, these probabilities, all of them have one thing in common. We're calculating the probability that x equals a specific value. But sometimes it's useful to have what's called a cumulative probability, which means less than or equal to a specific number. So, for example, with the coin flipping experiment, we could, for example, ask ourselves a question like this. By the way, I just realized I put P up there in the header. It's supposed to be, in this book, they're using F. So it means the same thing. Let me just go change that. It's a hard habit to break. All right, so let's change that to an F. I seem to misplaced my, oh, here it is. Yeah, just to be consistent, the book is using F of X. We may as well stick with it, but it's just that all the other books I've ever used P, so it's going to take me a while to get used to that. All right, here it is again. Now, here's what I want to do. What if I wanted to know the probability and this is again the case where we flip the coin 4 times of getting, let's say, 2 heads or less. Or you could write it out like this. Oh, and again, let's use F. So that would mean is actually the same thing as saying what's the probability of getting 0 heads plus 1 head plus 2 heads. 0.0625, so 0.25 plus 0.0625 equals 0.375. So because this is two heads or less, it's referred to as a cumulative probability. So what they're encouraging us to do is actually create an entire chart of cumulative probabilities. And so we're going to do that right here on sheet 2. This is a case where we have 10 trials and the probability of success is 0.3. So in order to do this, we're going to first calculate the actual individual probabilities with our binomial formula. Binom.dist, the number of successes is X, comma, number of trials is D1, and the probability of success is D2. Cumulative is, for this column, it's 0. And by the way, this is scientific notation. It's so close to 0 that they wrote it like this. This is 5.9049 e to the times 10 to the minus 6. So if we add these up, there might be a rounding issue here. Let's see what happens. No, it's fine. All right, now the cumulative. Oh, that's weird. It doesn't seem to want to fill in my graph. I don't know what's going on here. There it is. I don't know what it was thinking, maybe. So those are the actual probabilities. Now, cumulative means less than or equal to. So here's what you can do. Binom dist. Like before, number of successes is X. Number of trials is D1 with dollar signs. Probability of success is D2 with dollar signs, but now cumulative is 1. In Excel, that means yes, okay, or true. So let me show you that one more time. So you notice how at the end there it says 1. That's the cumulative part of it. And so by putting a 1 there, that means yes, I do want cumulative probabilities. Over here, we had a 0 for no. All right, so remember that. In Excel, 0 is no, 1 is yes. So when you drag this down, so this one, for example, is the probability that X is 2 or less, 4 or less, 5 or less. And so the graph looks like this. Uh-huh. The bars keep getting taller because each one of these is a less than or equal to probability. And sometimes that's what we're looking for. Okay, so like imagine that this is some kind of a game in a casino, and the only way you're going to win money is if the number of heads or the number of whatever is turning up is 3 or less. So we can easily calculate that probability. All right, so cumulative probabilities, you don't see them maybe as often, but it's awfully important. In some applications, this is what we're really interested in. But if not, if we're only interested in the individual probabilities, then we can use this approach. In the calculator, by the way, I almost forgot to mention, I briefly alluded to this earlier. To compute cumulative probabilities, for the binomial distribution, on the TI-84, you're going to do something slightly different. So let us return to the example of this coin flipping experiment, and let's calculate the probability that X is less than or equal to 2. So you will use, instead of binomial PDF, if you go back to second vars, you'll go down the list again, and this time you'll notice, like we did before, that after the binomial PDF, we have B binomial CDF. C stands for cumulative. That's all you have to do differently. Just choose CDF instead of PDF. So if I want to know the probability that the number of heads is two or less, instead of calculating each of these individually and adding them up, all I have to do is go to this binomial CDF function. And if you notice, it's asking the exact same questions. Trials, or P is a half. Remember, this is back to the quantum focusing experiment. And then X value is 2. But remember, this means 2 or less. It doesn't mean 2. 2 or less. And let's see what it tells us. 0.6875. So if we go look at our chart, we can confirm this. By doing the following. We're going to add these up. Okay. So in other words, 0.0625 plus 0.25 plus 0.062, sorry, 375. And let's see what we'll get. Point 6875. What do you know? All right. So in other words, there's always more than one way of getting the same results. We can calculate the individual probabilities and add them up, or we can use Excel's functionality, or with the calculator, we simply switch to this one instead of A, which is PDF. Now, having said that, you want to be careful. Make sure you don't get them backwards. All right. If you need PDF, use PDF. If you need CDF, make sure you use it. It would be very simple and easy to get them backwards. Don't do that. Okay. Be very, very careful. All right. Now, by the way, here's an interesting twist. It turns out that if you're using the binomial distribution, um, suppose you need to know the moments in this case. And remember, so this is, we're going back to the number of heads when we flip the coin 4 times. Okay, so X is a random variable, which means it has its own set of moments. So it has its own probability distribution, which happens to be the binomial distribution. And it has its own moments, which are, of course, the mean or expected value, variance, and standard deviation. Now, remember, we introduced those formulas a while back, and they were kind of messy. Well, it turns out that the binomial distribution, there are shortcut formulas we can use. or calculating measures. And what are they? So what I'm going to do is put together a little chart here to remind you what the original formulas look like and what the shortcut formulas look like. All right, so let's do this. So remember, we had to go through all the x's and multiply them by their probabilities. Here, we just put NP. I think you'll agree that's a lot faster. Here we have a very messy formula. Here we have, oh my God, is that all there is to it? Yes. And here, this part never changes. Let's just take the square root. So for the coin flipping experiment, n is 4, p is 0.5. So the expected value, or the number on average of heads we should get when we flip the coin twice, is 4 times 0.5, which is 2, and that makes perfect sense. Every time I flip the coin 4 times, I should expect to get 2 heads on average. The variance is a little bit trickier. It ends up being 1. And then the standard deviation is also 1, which is unusual. Normally, they don't equal each other. So that's what this part is all about. We're showing you the moments. And now this is for that case with the customers in the store. So remember, with that case, Mark's clothing store N is 3, and the probability of a customer buying is 0.3. So they're showing you how to calculate, in that case, the expected value, NP is 0.9. The variance, oh, and by the way, if you notice, sometimes for when they are writing about the variance of a random variable, they use VARX. It means the same thing as sigma squared. Then that is n times p times 1 minus p, which is 0.63, and then the square root of that, the standard deviation, is 0.79. Beautiful. So we've said everything we need to say at the moment about the binomial distribution. Now, then in the next session, we're going to look at this Poisson distribution, where the focus is a little different. Instead of visualizing this as a series of trials, what we're instead doing is observing the passage of time. And we're trying to figure out the probability that a certain number of events occur during that passage of time. For example, imagine yourself watching ships go down towards the Brooklyn Bridge, and you're trying to figure out the probability that during any given hour, there might be 6 ships passing underneath the Brooklyn Bridge. So it's very different than the binomial distribution, which is based on trials. Here, instead, we simply observe the passage of time, and we try to figure out the probability that a certain number of events occur during that time interval. So of necessity, the formulas will be a little different. And then I'll show you how to do this with an algebraic formula with the calculator itself, the TI-84's built-in functionality, and then finally Excel. We'll also see how to do cumulative probabilities. And then at the end, we'll also see how to calculate the moments, because here we also have special shortcut formulas. Now, I think that there's actually another. Yeah, so I just want to mention right up front, we're not going to be doing this one right here. It's very messy. It's not nearly as important as the other two. And so this will not appear in your MindTap assignments. It'll not appear in your your homeworks. I mean, your exams. So we're going to skip over it in the interest of time, and then move on to the next chapter. As soon as we're done with Poisson, we're going to skip ahead and then go right into chapter 6. Okay. So anyway, so we'll stop right here, and then the next time we meet, we'll quickly run through the Poisson distribution, and then we'll start chapter 6. Okay, so I'll see you then.